Our universe is hiding profound secrets in its ancient light and empty spaces. We are embarking on a journey through 30 of the most bizarre enigmas of cosmic evolution, a voyage that will transform how you see reality itself. By the end, you will grasp how solving these puzzles is the key to humanity's future among the stars. What triggered the Big Bang's first impossible second? And why is an invisible force tearing the cosmos apart? How we answer these questions will dictate the technologies we build and the civilizations we become. What single cosmic mystery keeps you wondering about our place in it all? That first second of existence remains the ultimate locked door. We call the event the Big Bang, but the name is misleading. It was not an explosion in space, but the sudden, violent emergence of space and time themselves. Within that initial, unimaginable fraction of a second, a process known as cosmic inflation occurred. The entire universe we can observe today, all 100 billion galaxies, expanded from a region smaller than a single proton to a colossal size, and it did so faster than the speed of light. Think of blowing up a balloon to the size of the entire Earth in the time it takes to blink. Now imagine that balloon is reality itself. This was not a violation of physics, but a reshaping of the very fabric of the cosmos, a period of hyper-expansion that smoothed out the universe and planted the seeds for all future structure. Yet for all its explanatory power, inflation only deepens the central mystery. What was the universe like before this event began? What flipped the switch, initiating this impossible growth spurt? We are left staring at a blank page in the cosmic history book, a page that holds the answer to why anything exists at all. The search for that answer leads us directly to our next great cosmic puzzle, one hidden in the faint afterglow of creation itself. That initial burst of expansion left behind a permanent signature, a whisper of heat from the universe's fiery birth. We can still detect that cosmic microwave background radiation today, a faint glow that fills all of space. Yet this afterglow revealed something far stranger than anyone expected. The way galaxies spin and move within clusters defies all logic based on the matter we can see. Stars at the outer edges of galaxies orbit just as fast as those near the center, a behavior that shatters the predictions of gravity. It is as if every visible galaxy is merely the glittering tip of a vast, invisible iceberg. The only explanation is that a mysterious, unseen substance we call dark matter provides the extra gravitational glue. This invisible scaffold holding the cosmic architecture together makes up over 85% of all the matter in the universe. We feel its gravitational pull, we map its ghostly contours, but we have no idea what it is. It does not emit, absorb, or reflect any form of light, making it completely transparent to our telescopes. So what could this fundamental component of reality possibly be made of? The leading candidates are as bizarre as the phenomenon itself. One possibility involves weakly interacting massive particles, or WIMP. These are hypothetical particles that are heavy, yet interact with normal matter only through gravity and the weak nuclear force, making them incredibly difficult to detect. Billions of these particles could be passing through your body every second without a trace. Another compelling candidate is the action, an ultra-lightweight particle born from theories attempting to solve other deep puzzles in quantum physics. Actions would form a strange, wave-like sea throughout the cosmos. The true nature of dark matter is not just an academic curiosity. Solving this mystery is a race that involves the most advanced technology on and off our planet. Deep underground, in abandoned mines shielded from cosmic rays, incredibly sensitive detectors wait for the once-in-a-lifetime bump of a WIMP collision. In space, powerful telescopes like the James Webb scan the way light bends around massive galaxy clusters, creating detailed maps of dark matter's invisible web. And in enormous particle colliders, scientists attempt to create this elusive substance by smashing ordinary particles together at nearly the speed of light. The prize for discovering what dark matter is made of is nothing less than a new chapter in physics. It would reveal a fundamental ingredient of the universe that has been hidden from us since the beginning, a secret component that literally holds our reality together. And this quest for the invisible leads us directly to an even more perplexing force, one that operates on the grandest stage of all. But the invisible scaffolding of dark matter is only half the story. A far more potent and bizarre force is at work on the cosmic stage. For decades, astronomers believed the universe's expansion was slowing down, a natural coasting after the Big Bang's initial push. Then, in the late 1990s, two independent teams made a discovery so shocking it earned them the Nobel Prize. They were observing distant, dying stars called supernovae to measure how much the cosmos had braked over billions of years. Instead, they found the opposite. The expansion of the universe is not slowing at all. It is speeding up. Something is forcefully and relentlessly stretching the very fabric of space itself. We call this mysterious something dark energy. It is the dominant component of our universe, making up a staggering 70% of its total energy budget. Think of it like this: if you throw a ball into the air, you expect gravity to pull it back down. But what if the ball not only kept rising, but shot away faster and faster into the sky, defying all logic? That is precisely what dark energy is doing to our cosmos. Galaxies are being pushed apart from one another at an ever-increasing rate. So what could possibly be causing this cosmic repulsion? One leading idea is that dark energy is an intrinsic property of empty space itself. Empty space is not truly empty, according to quantum physics. It is a seething, bubbling foam where virtual particles pop in and out of existence. This vacuum energy could generate a constant, repulsive force, an idea first proposed by Albert Einstein as his cosmological constant. The problem is, when physicists calculate the expected strength of this vacuum energy, the number they get is wrong by a factor of 1 followed by 120 zeros. It is the worst theoretical prediction in the entire history of science. This colossal failure suggests we might be missing something profound. Perhaps dark energy is not a constant at all, but a dynamic field that changes over time, a sort of cosmic fluid with negative pressure. We have named this concept quintessence, but its true nature remains entirely speculative. The most radical possibility of all is that dark energy is not a force, but a sign that our understanding of gravity, the very framework of general relativity, is incomplete on the largest scales. Could Einstein's theory need a revision that reveals a new kind of repulsive gravity? The implications of this mystery are not just philosophical. They dictate the ultimate fate of everything. If dark energy remains the dominant force, it will lead to a cold, lonely, and isolated end for the cosmos. In tens of billions of years, the acceleration will become so fierce that distant galaxies will be ripped beyond our cosmic horizon. Their light will never reach us again. The universe will become a vast, expanding emptiness with island galaxies drifting alone in an ever-darkening void. Solving the puzzle of dark energy is therefore a race to read our own ultimate destiny, and this accelerating expansion forces us to confront an even more fundamental question about the very laws that govern our reality. This accelerating cosmic fate rests on a razor's edge, a balance decided in the universe's very first moments. For there is a deeper mystery, one that makes our very existence a statistical miracle. According to our best theories, the Big Bang should have created equal amounts of matter and antimatter. Think of them as cosmic twins, born together but locked in a fatal embrace. For every particle of matter, like an electron or a quark, an antimatter counterpart was created. The problem is, when matter and antimatter meet, they annihilate each other in a flash of pure energy. They are perfect opposites, so in that initial seething furnace of the newborn cosmos, all the particles and antiparticles should have found each other. Every single pair should have mutually destructed, leaving behind a universe containing nothing but a dull, expanding fog of light. There would be no atoms, no chemistry, no stars, no planets, and certainly no one to wonder about it. Yet here we are. The fact that you can hear these words means this total annihilation did not happen. A tiny, almost insignificant sliver of matter survived. For every 1 billion antimatter particles, 1,000,000,001 matter particles must have been created. That 1 in a billion imbalance is the reason anything exists at all. Every galaxy, every star, every planet, and every one of us is made from the leftover ashes of that near-total cosmic self-destruction. So what cosmic rule was broken to allow this surplus of matter to survive? Physicists call this the mystery of charge parity violation, or CP violation. In simple terms, it means that the laws of physics treat matter and antimatter slightly differently. It is as if the universe has a tiny, built-in bias, a preference for one type of particle over its mirror image. We have observed this slight asymmetry in the lab with certain exotic particles, but the effect is far, far too small to account for the overwhelming dominance of matter we see in the cosmos today. The known violations are a mere trickle, not the flood we need to explain our existence. This means something fundamental is missing from our picture. Perhaps there are undiscovered forces or particles that acted only in that first fleeting instant, tipping the scales decisively in favor of matter. Maybe entire galaxies made of antimatter exist in distant, isolated regions of space, though observations suggest our entire observable universe is made overwhelmingly of matter. The search for the source of this bias is a hunt for new physics, conducted in massive underground laboratories and powerful particle colliders. Scientists are meticulously studying the behavior of the most unstable particles, looking for any tiny deviation, any other crack in the symmetry that might reveal the hidden mechanism that saved the universe from total oblivion. Solving this is not just about our origins, it is about understanding if the existence of complex structures like us was a freak accident or an inevitable outcome of the cosmos's fundamental rules. And this question of cosmic bias leads us to wonder if the very constants of nature were also fine-tuned for life. That 1 in a billion surplus of matter gave our universe its raw material, the cosmic dust from which everything would eventually form. But for hundreds of millions of years, the cosmos remained in a state of profound darkness. A vast, featureless soup of hydrogen and helium gas, still glowing faintly from the Big Bang's heat, was all that existed. There were no stars, no galaxies, and no light to see them by. Then a revolution began. From this primordial gloom, the very first stars ignited. These were not like the stars we see today. They were behemoths hundreds of times more massive than our sun, and they burned with a ferocious, brilliant blue intensity. Their birth was the cosmic dawn, the moment the universe woke up and turned on the lights. This transformation did not happen gently. The intense ultraviolet radiation from these first stars and early galaxies began to tear apart the surrounding atoms of neutral hydrogen gas that filled all of space. Think of a dense, pervasive fog suddenly being burned away by the rising sun. This pivotal period is what astronomers call the epoch of reionization. It was the universe's great unveiling as these first luminous objects systematically cleared away the cosmic fog, making the vast reaches of space transparent to light for the very first time. Observing this ancient era is one of the greatest technological challenges in all of modern astronomy. The light from that time has been traveling for over 13 billion years to reach us. It has been stretched and redshifted by the expanding universe. Its waves lengthen from visible light into faint radio signals. Catching this whisper from the dawn of time requires instruments of incredible sensitivity. We are building colossal radio telescope arrays in some of the most remote and radio-quiet places on Earth, like the deserts of Chile and the high plateaus of Western Australia. These telescopes are not single dishes, but vast fields of simple antennae spread across miles of terrain, working in concert to form a single, giant ear listening to the cosmos. They are trying to detect a specific, subtle signal from the neutral hydrogen that existed before and during reionization, a faint dip in the radio spectrum that is 1,000,000 times quieter than the interference from our own television broadcasts and satellites. It is like trying to hear a single snowflake land in the middle of a roaring rock concert. The prize for succeeding is a direct window into the universe's childhood, a chance to watch the very first structures flicker to life. What triggered the formation of those first stars in the dark? Why did they clump together to form the earliest galaxies? The answers are hidden in that faint radio hum waiting to be decoded. And as we push our technology to its absolute limits to hear that ancient story, we must also confront an even more elusive cosmic architect, one that wrote the blueprints for all of this structure in the very first moments. That great unveiling of the cosmos revealed a structure far more intricate and organized than anyone could have predicted. The universe is not a random scattering of galaxies, but a magnificent, sprawling architecture. We call it the cosmic web. Imagine gazing upon a colossal spider's web glistening with morning dew, its silken threads stretching for millions of light years. At the intersections of these threads, you find dense knots of brilliant light, the galaxy clusters. Connecting them are the long, delicate filaments, rivers of galaxies and dark matter. And between it all, spanning the majority of the volume of the universe, are the immense, terrifyingly empty voids. This is the true large-scale structure of our reality, a foam-like pattern written into the fabric of space. But why did the universe choose this particular form? The blueprint was drawn in the first fraction of a second, imprinted upon the cosmos by those quantum ripples from the inflationary period. These tiny, random fluctuations in density were the seeds of all future structure. Where there was a tiny bit more matter, gravity had a slightly stronger grip. Over billions of years, gravity acted as a cosmic sculptor, tirelessly amplifying these small differences. It pulled matter from the emptier regions into the denser ones, weaving the dark matter into a vast, invisible skeleton. The ordinary matter, the gas and dust that would become stars and galaxies, simply flowed along this pre-established gravitational landscape, lighting up the web like fairy lights on a dark tree. Yet this cosmic tapestry is not a uniform pattern. It contains structures of such immense scale they defy easy explanation. One of the most famous is the Boötes Void, a spherical region of space so empty it has been called the Great Nothing. Stretching across 250 million light-years, this void is so vast that if our own Milky Way galaxy sat at its center, we would have had no idea other galaxies existed until the 1960s. In a universe that should be roughly similar everywhere, how did such an enormous pocket of near-nothingness form? The voids are not completely empty, of course. They contain a few isolated galaxies like lone ships adrift in an endless, dark ocean, but their sheer size presents a puzzle. Did they form from the collapse of underdense regions in the early universe, or is there a more exotic process at work? The cosmic web and its voids tell us that the initial conditions of the universe were not perfectly smooth, and that gravity's relentless work over eons has created a reality of stunning beauty and profound mystery. This grand architecture forces us to look closer at the individual building blocks, the galaxies themselves, and ask how they took on their majestic forms. Those majestic galaxies, woven into the cosmic web, are threaded with invisible forces of their own. Deep within the swirling gas between the stars, and even in the vast emptiness between galaxies themselves, magnetic fields stretch for millions of light years. These are not the simple fields of a bar magnet, but complex, dynamic structures that twist and turn through the void. We can map them by observing the way they polarize the light from distant quasars or by studying the subtle alignment of cosmic dust grains. But their existence presents a profound puzzle. Where did these cosmic magnets come from? The problem is a classic chicken and egg scenario. Magnetic fields are generated by the movement of electrically charged particles, like those in a hot plasma. But to get a large-scale magnetic field started, you need a tiny seed field to amplify. It is like trying to start a car with a dead battery. You need a little jump of energy to get the engine turning over. So what provided the universe's first magnetic jump start? One compelling theory reaches back to the universe's infancy. In the violent chaos of the first second, during the period of cosmic inflation, incredibly powerful energy fields could have generated the first primordial magnetic fields. These seed fields, weaker than the magnetic field of a refrigerator magnet, would have been stretched across the entire cosmos as space itself expanded. They would have been there from the very beginning, a faint imprint waiting for the universe to give them form. An alternative idea suggests that the first stars and galaxies themselves were the architects. As the first massive stars lived their short, violent lives and then exploded as supernova, they churned the surrounding gas, creating turbulent motions. This stellar dynamo, much like the one that generates Earth's own magnetic field, could have amplified tiny, random magnetic fluctuations into the organized fields we see today. The truth might be a combination of both, a partnership between a primordial whisper and stellar amplification. Solving this mystery is far more than an academic exercise. These cosmic magnetic fields play a crucial role in the evolution of galaxies. They help channel gas flows, influence the birth of new stars, and even accelerate cosmic rays to nearly the speed of light. For our own future, understanding them is a matter of practical survival and ambition. The space between stars is not empty, it is filled with this magnetized plasma. For future spacecraft traveling at a significant fraction of light speed, these fields would be like invisible reefs in an ocean, deflecting and focusing dangerous high-energy particles. A detailed map of the galactic magnetic field would be as essential for interstellar navigation as a nautical chart is for a ship's captain. Furthermore, if we ever hope to use neutrinos or gravitational waves for cosmic communication, we will need to understand how these magnetic fields distort and affect their journeys. The invisible force that helped shape the galaxies may one day guide our own ships through them. And just as these fields sculpt the large-scale structure of the cosmos, other, more violent events forge the very elements that make our world possible. Our invisible cosmic architecture, forged by gravity and magnetism, ultimately rests on a single, precarious balance. The fate of everything we see and everything we are depends on a silent war being waged between two fundamental forces. On one side is gravity, the Great Attractor pulling matter together to build galaxies, stars, and planets. On the other is dark energy, the mysterious repulsive force accelerating the expansion of the cosmos itself. The ultimate destiny of our universe hinges on which of these titans wins this cosmic tug of war. The evidence we have gathered so far points toward three profoundly different endings, each more strange and final than the last. The first and currently the most favored scenario is the Big Freeze, also known as heat death. In this future, dark energy remains dominant and constant. The acceleration of the universe continues unchecked, growing ever more fierce over trillions upon trillions of years. One by one, the stars will burn through their fuel and wink out, leaving behind cold, dead remnants like black dwarfs, neutron stars, and black holes. Galaxies will be torn apart as the expansion of space itself overcomes their gravitational bonds. Eventually, even these stellar corpses will decay through a process known as Hawking radiation, slowly evaporating into nothingness. The universe will become an ever-cooling, ever-expanding void, a near-perfect vacuum where the temperature approaches absolute zero. In this eternal, dark stillness, no energy gradients will remain, no work can be done, and no form of complex life or intelligence could possibly exist. It is a quiet, drawn-out end to all activity. But what if dark energy is not constant? What if its repulsive power grows stronger over time? This possibility leads to a far more violent and dramatic finale, the Big Rip. In this scenario, the force of dark energy intensifies to the point where it does not just push galaxies apart. It begins to tear apart everything bound by gravity, and then everything bound by the other fundamental forces. First, galaxy clusters would be shredded. Then, individual galaxies themselves would be pulled apart. As the end draws near, the accelerating expansion would rip stars from their solar systems. Planetary systems would be torn asunder. In the final, terrifying moments, planets and stars would be ripped apart atom by atom. The very fabric of space-time would be stretched beyond its limits, shredding molecules, nuclei, and even the fabric of reality itself. The universe would end not with a whimper, but with a catastrophic, instantaneous disintegration of all structure. Is there any hope for a cyclical universe, a cosmic rebirth? This brings us to the third classic scenario, the Big Crunch. For this to happen, dark energy would have to weaken or reverse, allowing gravity to finally regain the upper hand. After trillions of years of expansion, the universe would slowly begin to contract. Galaxies would start rushing back toward each other. The cosmic background radiation, now a cold whisper, would begin to heat up as space compresses. The sky would glow ever brighter and hotter as the universe collapses in on itself. The end would be a mirror image of the Big Bang, a fiery collapse into an ultra-hot, ultra-dense singularity. This singularity could, in theory, become the seed for a new Big Bang, birthing a brand new universe in an endless cycle of cosmic death and rebirth. The evidence, however, currently weighs heavily against this cyclical model. Our observations of distant supernova and the cosmic microwave background strongly suggest that dark energy is here to stay, and that its effects are constant or even strengthening, making a big crunch increasingly unlikely. So what does this mean for the long-term future of life and intelligence? The timescales involved are almost incomprehensibly vast. A technological civilization that arose billions of years from now might look up at a completely black sky, their island galaxy having been isolated from all others by the accelerating expansion. They would have no evidence that other galaxies ever existed, no clue to the true nature of the cosmos's origin. Their universe would be a single, lonely galaxy drifting in an eternal void. This presents the ultimate challenge for intelligence. Could any form of mind, no matter how advanced, find a way to survive the end of stars, the decay of matter, or the very unraveling of space-time? The answer to that question forces us to confront the next great mystery, one that asks whether the universe itself might be fine-tuned to allow for our existence. This profound question of our cosmic fate is rooted in a much earlier mystery, one written in the faint, uniform glow of the universe's infancy. When we observe the cosmic microwave background, the oldest light in existence, we find something deeply puzzling. No matter which direction we point our telescopes, this afterglow has almost exactly the same temperature. It is uniform to within 1 part in 100,000. This means that regions of the universe now separated by billions of light years were once in perfect thermal equilibrium, as if they had been in intimate contact. And that is precisely the problem. According to the standard Big Bang model without inflation, there has not been enough time since the beginning of the universe for light or heat to have traveled between these vastly distant regions. They lie outside each other's cosmic horizons, meaning they could never have exchanged information or energy to achieve this uniform temperature. It is as if you met a perfect stranger on the other side of the world, and you both discovered you were wearing identical outfits down to the smallest thread without ever having communicated. How could such perfect coordination occur? This is the horizon problem, and it suggests that our classical understanding of the Big Bang is incomplete. The most compelling solution takes us back to that explosive first fraction of a second, to the theory of cosmic inflation. Inflation proposes that before the universe was even 1/1,000,000,000 of a trillionth of a trillionth of a second old, it underwent a period of hyper-expansion, ballooning from a subatomic speck to a size larger than our entire observable universe. This incredible growth spurt would have taken a tiny, causally connected patch of space, a region where every part had time to interact and settle into a uniform temperature, and stretched it to become the entirety of the cosmos we can see. What we perceive as distant, disconnected horizons today were once nestled right up against each other in that primordial speck. Inflation solved the horizon problem by giving the entire observable universe a shared, intimate past. Yet this elegant solution raises an even more staggering possibility. If our entire observable universe, all 100 billion galaxies, came from one tiny, inflated patch, then what lies beyond our cosmic horizon? The true scale of the entire cosmos could be unimaginably vaster. Inflation may not have been a one-time event, but an eternal process, creating a multiverse where countless other bubble universes, each with potentially different physical laws, are continuously being born. Our universe, with its specific constants and conditions, might be just one island in an infinite cosmic archipelago. We are forever isolated from these other realms by the relentless expansion of space itself, their light forever beyond our reach. This leaves us with a haunting question. Are we studying the unique properties of a single universe, or are we merely sampling the local conditions of one tiny pocket in a much grander, and perhaps infinite, reality? This perfect uniformity across the cosmos hints at an even deeper fine-tuning, one written into the very geometry of space itself. Our universe is not just thermally even, it is geometrically flat. This is not flat like a sheet of paper, but flat in the sense of its large-scale curvature. In a closed or positively curved universe, parallel lines would eventually meet, like lines of longitude on a globe. In an open, negatively curved universe, they would diverge forever. But in a flat universe, parallel lines remain perfectly parallel, and the rules of classic Euclidean geometry we learned in school hold true on the grandest of scales. Measurements from the cosmic microwave background and distant supernova have confirmed with stunning precision that our universe is flat to within a margin of error of just 0.4%. This presents a monumental puzzle known as the flatness problem. For the universe to be this flat today, its initial conditions at the Big Bang had to be fine-tuned to an absurdly specific degree. Think of balancing a pencil perfectly on its sharpened tip. The slightest nudge, the tiniest imperfection, and it topples over. Now imagine balancing that pencil not for a second, but for 13.8 billion years. The initial density of the universe had to be so precisely calibrated to a critical value that even a deviation of 1 part in 10 to the power of 60, that is a 1 followed by 60 zeros, would have resulted in a cosmos that either collapsed back on itself immediately or expanded into a thin, unrecognizable void. The odds of such a perfect balance occurring by random chance are virtually zero. So how did our universe achieve this impeccable equilibrium? The most powerful explanation, once again, lies in the theory of cosmic inflation. That hyper-expansion in the first fraction of a second acted like a cosmic iron, stretching the fabric of space so violently that it smoothed out any primordial curvature. No matter what shape the universe was born with, whether wildly curved or crumpled, inflating it to such an enormous size would make it appear perfectly flat from our local human perspective. It is the same reason the surface of the Earth appears flat to us standing on it, even though we know it is a sphere. When you zoom in on a small enough patch of a curved surface, it looks flat. Inflation took a potentially tiny, curved patch of the primordial universe and expanded it to become our entire observable cosmos, making its local geometry indistinguishable from perfect flatness. This makes the flatness problem a cornerstone of modern cosmology, not just as a solved puzzle, but as powerful evidence for the inflationary paradigm itself. Yet this elegant solution raises a profound new question. If inflation stretched our local universe into flatness, what is the true, global shape of the entire cosmos beyond our horizon? We may simply be living in a tiny, flattened region of a reality whose ultimate geometry remains forever hidden from our view. This geometric perfection of our universe, forged by inflation, should have left behind a specific kind of cosmic relic, a fossil from that era of unification. According to our most ambitious theories of physics, the universe's fundamental forces were once a single, unified power. As the cosmos cooled and expanded, this superforce underwent a series of phase transitions, like water freezing into ice, splitting into the distinct forces we know today: gravity, the strong nuclear force, the weak nuclear force, and electromagnetism. These theories, known as grand unified theories, make a firm prediction. One of the inevitable byproducts of this cosmic splitting should be a profusion of magnetic monopoles. A monopole is a hypothetical particle that is a solitary magnetic pole. Think of a magnet from your refrigerator. It always has a north and a south pole. If you break it in half, you do not get isolated poles. You get two smaller magnets, each with its own north and south. A true magnetic monopole would be different. It would be a particle that is just a north pole with no accompanying south or vice versa. These objects are not just scientific curiosities, they are expected to be incredibly massive, potentially as heavy as a bacterium, which is an enormous mass for a single subatomic particle. The puzzle is that despite decades of searching, we have never convincingly found one. They are nowhere to be seen, so where did all the monopoles go? The most elegant solution is once again cosmic inflation. The theory suggests that the phase transition that created the monopoles occurred just before or during the inflationary period. At that moment, a dense sea of these massive particles would have been generated, but then inflation kicked in. The universe underwent that incredible hyper-expansion, stretching space by a factor of trillions upon trillions. This would have diluted the monopoles to such an extreme degree that their average density in our observable universe became virtually zero. The entire cosmos we can see might contain only a handful of these relics, making the chance of one ever passing through a detector infinitesimally small. It is as if you had a single grain of sand and scattered it across the entire volume of the Earth. The odds of finding that specific grain are astronomically low. This makes the missing monopoles a powerful, if indirect, piece of evidence for inflation itself. Their absence is precisely what the theory predicts. Yet the hunt is not over. The discovery of even a single magnetic monopole would be a monumental event in physics. It would be direct proof that grand unified theories are on the right track, providing our first tangible evidence of physics beyond the standard model. Such a discovery would not just rewrite textbooks, it could open up entirely new technological frontiers. The unique properties of a monopole could, in theory, be harnessed. Some physicists speculate that arrays of monopoles could be used to create force fields to shield spacecraft from cosmic radiation, or even to construct new types of energy generators that are far more efficient than anything we have today. The energy locked within their structure could be immense. The continued search for these elusive particles is a testament to our drive to understand the universe's deepest symmetries, a hunt for a missing piece of cosmic history that could one day power our future among the stars. That same invisible hand that sculpted the galaxies may have left its signature much closer to home, in the silent, dark expanse beyond Pluto. For decades, two robotic pioneers, the Pioneer 10 and Pioneer 11 spacecraft, were steadily drifting toward the outer solar system after completing their historic missions to Jupiter and Saturn. As they traveled farther from the Sun than any human-made object had before, scientists tracking their precise trajectories noticed something deeply perplexing. Both spacecraft were experiencing a tiny but persistent and identical deceleration. It was an incredibly small pullback toward the Sun, an anomaly equivalent to just 1/10,000,000th of the gravity we feel on Earth's surface. Imagine a single sheet of paper resting on your hand. That is the kind of gentle, constant pressure slowing these probes down. For years, this pioneer anomaly defied all conventional explanation. Was it the gravitational pull of unseen, dark matter clustered in our solar system? Could it be a subtle flaw in our understanding of Einstein's theory of general relativity? A hint that gravity behaves differently in the deep, cold emptiness of interstellar space. The mystery captivated physicists and engineers, suggesting that our map of the fundamental forces might have a tiny, unexplored corner. The solution, when it finally came, was a triumph of meticulous engineering over exotic physics. A team of researchers spent years recovering old data and analyzing the spacecraft's own design. They discovered that the heat generated by the probe's radioactive power sources and their onboard electronics was being radiated away from the spacecraft. This thermal radiation, while incredibly weak, was acting like a tiny, constant photon thruster. Just as the gentle stream of air from a balloon pushes it forward, the steady stream of infrared photons pushing off the back of the spacecraft was generating a minute but continuous force, perfectly accounting for the observed deceleration. The Pioneer anomaly was not a breakdown of physics, but a lesson in thermal engineering on a grand scale. Yet its legacy is far more profound than a simple solved puzzle. It demonstrated with stunning clarity that even the most well-tested laws of physics must be scrutinized when we operate in new environments. For future missions destined for interstellar space, like the Voyager probes now flying through the void, accounting for every watt of heat, every photon of radiation, is essential for precise navigation. The anomaly stands as a permanent cautionary tale, reminding us that the greatest mysteries are sometimes hidden not in the laws of nature, but in the intricate details of our own technology. This relentless pursuit of precision, born from a decades-long cosmic detective story, now guides our search for the most elusive ripples in the fabric of reality itself. Yet the very uniformity of this cosmic background holds a strange and unsettling flaw. When scientists created exquisitely detailed maps of this primordial light, they expected to find a random, featureless pattern, a final confirmation of the cosmological principle that the universe is the same in all directions. Instead, they found something that should not be there. A mysterious, large-scale alignment seems to streak across the sky, an axis that some researchers have dramatically nicknamed the axis of evil. This is not a malevolent force, but a statistical anomaly in the temperature fluctuations of the cosmic microwave background. The hot and cold spots appear to be subtly aligned along a particular direction in space, as if the entire universe has a faintly preferred orientation. This discovery is profoundly controversial because it directly challenges one of the most sacred tenets of modern cosmology, the idea that the universe is isotropic, meaning it has no special direction. It suggests our cosmos might have a discernible spin or a tilt on the largest scales imaginable. How could the entire universe possibly have an axis? The statistical significance of this alignment is the heart of the debate. In simple terms, scientists calculate the odds that such a pattern could appear by pure random chance. The initial findings suggested the probability was less than 1 in 1,000, a result that would normally be considered significant in physics. But the cosmos is vast, and when you are analyzing a map with millions of data points, unusual patterns can and do emerge simply through the sheer size of the dataset. It is like finding a face in the clouds, a pattern your brain imposes on random water vapor. Skeptics argue this is precisely what the axis of evil is, a cosmic mirage, a statistical fluke that will vanish as our measurements become more precise. Yet, the anomaly has stubbornly persisted, even in data from the most advanced space telescopes. If it is real, the implications are staggering. It could mean that our universe is not perfectly uniform after all, that its expansion or initial conditions were ever so slightly lopsided. Some theorists have proposed even more radical explanations. Could this axis be a fossil imprint from a time before the Big Bang, a scar from a collision with another universe in the vast multiverse? Perhaps the fabric of our reality was twisted by its violent birth, leaving a permanent, ghostly warp in the background radiation. The debate is far from settled, and it forces a fundamental question upon us. Are we seeing the first crack in our standard model of cosmology, a hint of a deeper, more complex reality, or are we merely witnessing the human tendency to find patterns in the noise? The answer will not come easily, and it pushes our observational skills to their absolute limit. This perfect cosmic geometry hides a fundamental flaw in our understanding of the universe's first chemical elements. In the initial fiery minutes after the Big Bang, the cosmos was a primordial nuclear furnace, forging the very first atomic nuclei in a process we call Big Bang nucleosynthesis. Our models of this brief, explosive period predict with stunning accuracy how much of the universe should be hydrogen and helium. The observations of these ancient elements in the oldest stars and gas clouds match the predictions almost perfectly. But there is one glaring exception: lithium. The models tell us there should be about 3 times as much lithium in the oldest stars as we actually observe. This is the lithium problem, a small but persistent crack in our otherwise successful story of the universe's first moments. Think of it as a cosmic recipe that has been tested and retested, where every ingredient seems to work perfectly, yet the final cake consistently comes out missing one specific flavor. For decades, astronomers have been searching for this missing lithium, scouring the atmospheres of ancient stars that formed from nearly pure primordial gas. These stellar fossils should preserve the chemical signature of the Big Bang itself. Yet, no matter where we look, the lithium abundance is always too low. So where did it go? One possibility is that our understanding of nuclear physics during that first frantic 3 minutes is incomplete. Perhaps there were unknown nuclear reaction pathways that destroyed lithium as quickly as it formed, or maybe the conditions of temperature and density were slightly different than we currently calculate. Another, more thrilling possibility is that the lithium problem is a clue pointing to new physics. The presence of exotic, undiscovered particles in the early universe could have altered the nuclear reactions. For instance, certain types of dark matter particles could have interacted with the primordial plasma, subtly changing the rates at which protons and neutrons fused, effectively erasing lithium from the cosmic ledger. Solving this puzzle is not just about accounting for a single element. It is a direct test of our most fundamental theories about the universe's origin. If the flaw is in the nuclear physics, we must refine our models. But if the culprit is a new type of particle, then the humble lithium atom becomes our guide to a world of physics that lies entirely beyond the standard model. This seemingly minor discrepancy in the cosmic accounting of a light metal could be the thread that, when pulled, unravels a much larger tapestry of hidden forces and particles, forever changing our view of creation's first moments. Our cosmic accounting of lithium reveals a universe that is almost, but not perfectly, predictable. This same tension between our maps and reality appears again on a scale so vast it is difficult to comprehend. We are all, right now, caught in a silent cosmic current. Our entire Milky Way galaxy, along with its neighboring galaxies, is being pulled through space at a staggering 2 million kilometers per hour toward a specific point in the distant constellations of Centaurus and Norma. The source of this immense gravitational pull is a mystery we call the Great Attractor. Imagine a waterfall hidden behind an impenetrable wall of fog. You cannot see it, but you can feel its powerful, irresistible tug on the river you are floating down. That is our situation. We are feeling the pull of something colossal, but our view of it is completely blocked by the dense band of stars, gas, and dust that constitutes the central plane of our own Milky Way galaxy. This region is known as the zone of avoidance because it effectively blinds our optical telescopes to the universe beyond. For decades, the Great Attractor was a ghost, a name for a gravitational signal with no visible source. What could possibly exert such a force? The initial suspicion fell on a massive, unseen concentration of dark matter, a gargantuan knot in the cosmic web whose gravity was reeling us in. As our technology advanced, allowing us to peer through the galactic smog with infrared and radio telescopes, a clearer picture began to emerge. We discovered that the Great Attractor is not a single, incomprehensibly dense object. It is actually the gravitational heart of our entire local supercluster, a structure we now call Laniakea, a Hawaiian word meaning immense heaven. Laniakea is a sprawling filament of over 100,000 galaxies, all bound together by gravity, and the Great Attractor is its central gravitational valley, the point toward which everything in our galactic neighborhood is slowly flowing. This resolves part of the mystery. The source of the pull is the combined mass of a vast supercluster, but a deeper puzzle remains. Even the immense visible mass of Laniakea does not fully account for the speed of our motion. There seems to be something even larger beyond it, an even more distant and massive conglomerate of galaxies, known as the Shapley supercluster, which is adding its own gravitational pull to the mix. So the Great Attractor is not one, but many, a cascade of gravitational influences from the largest structures in the universe. Our journey is a reminder that we are not still, but perpetually in motion, riding a river of gravity toward a point we once could not see, pulled by forces that stretch across hundreds of millions of light years. This grand motion forces us to wonder what other invisible currents shape the cosmos, and whether the very emptiness of space might hide structures even more immense. That silent cosmic river pulling our galaxy is a reminder of how much we listen for signals we cannot see. Decades ago, we pointed our own ears to the sky, hoping to catch a whisper from another civilization. And for one unforgettable moment, it seemed we had. On a hot August night in 1977, a radio telescope at Ohio State University known as the Big Ear was engaged in its routine scan of the heavens. The data was printed out on long, continuous sheets of paper, with columns of letters and numbers representing signal strength. A few days later, a volunteer astronomer named Jerry Amon was reviewing the printout. His eye was caught by a sequence of characters so startling that he circled it in red pen and wrote a single, powerful word in the margin. Wow! The signal, which lasted for 72 seconds, was a stunningly strong, narrowband radio burst. It came from the direction of the constellation Sagittarius, and it matched almost perfectly what scientists had predicted an artificial, interstellar transmission would look like. It was not the broad, messy signal of a natural cosmic event, but a clean, focused beam, concentrated on one specific frequency, the hydrogen line, which is 21 centimeters. This frequency is considered a universal landmark, a logical channel for any advanced civilization to use for communication, as hydrogen is the most common element in the universe. For that brief minute and 12 seconds, the WOW signal was over 30 times stronger than the background noise of space. It appeared, peaked, and then vanished, following the exact curve expected as the Earth's rotation swept the telescope's field of view across a fixed point in the sky. The immediate assumption was that this had to be a human-made signal, perhaps a reflected broadcast from a satellite or a piece of space junk. But a frantic investigation began, and every possible terrestrial and solar system origin was systematically ruled out. There were no satellites in that position, no known asteroids or comets, and no military tests that could account for it. The search for a repeat began in earnest. Astronomers pointed every available radio telescope back toward that same patch of sky, again and again, for months and then years. They scanned across a wide range of frequencies, hoping to catch another glimpse. The silence that followed was absolute. The signal never repeated. Its one-time, brilliant flash has fueled decades of speculation and debate. Could it have been an intercepted burst of communication between two alien civilizations? Perhaps it was a powerful, one-time beacon, sweeping through the galaxy like a lighthouse beam that illuminated Earth for a single, fleeting moment. Or maybe it was something entirely natural, a previously unknown astrophysical phenomenon that just happens to mimic an artificial signal with uncanny precision. The legacy of the WOW signal is profound. It stands as the most compelling, unexplained candidate in the history of the search for extraterrestrial intelligence, a tantalizing hint that we might not be alone. It taught us the importance of patience and the sheer, staggering scale of the cosmic ocean we are trying to fish in. Finding a signal is like hearing a single, distinct voice in a roaring stadium, only for the crowd to fall silent before you can locate the speaker. That one circled word on a sheet of computer paper continues to inspire new generations of astronomers and projects, a permanent symbol of the thrilling possibility that the next time we listen, the signal might just decide to speak again. That single, unanswered WOW signal echoes across a new frontier of cosmic whispers, signals so powerful they can outshine a billion suns for just 1,000th of a second. These are fast radio bursts, or FRB, and they are rewriting the rules of high-energy astronomy. Discovered only in 2007, these blasts are not gentle, repeating signals. They are cosmic gunshots, immense flashes of radio energy that travel across billions of light years to reach our telescopes. For a fleeting moment, an FRB can release more energy than our sun will emit over 80 years, all compressed into a blink so fast it defies human perception. The mystery begins with their origin. What natural engine could possibly be so powerful, so efficient, and so brutally brief? The leading suspects are some of the universe's most extreme objects. One compelling candidate is the magnetar, a type of neutron star with a magnetic field so intense it could erase a credit card from half the moon's distance away. A starquake on the surface of such a magnetar, a sudden cracking of its rigid crust, could unleash a titanic shockwave, rippling out into space as a brilliant, one-off radio flash. Other theories point to the cataclysmic collisions of dense stellar corpses, like two neutron stars spiraling into each other in a final, fatal dance. Their merger could produce a short, sharp burst of radiation as they collapse into a black hole. But the plot thickened when astronomers found something they never expected: a repeater. While most FRBs are one-off events, a few sources have been caught firing off multiple bursts, sometimes in chaotic, unpredictable patterns. This changes everything. A collision is a one-time event. You cannot have the same two stars crash together again and again. The repeaters suggest there must be a source that can survive its own outburst, a cosmic engine that can fire multiple times without destroying itself. This brings us to the most speculative and fascinating possibility on the fringe of science. Could some of these signals, especially the repeating ones, be artificial in origin? It is a question scientists must consider, however remote the chance. An advanced civilization might use stupendously powerful bursts of energy to propel light sails on interstellar ships. A single, focused FRB could, in theory, push a vast spacecraft to a fraction of light speed. Or perhaps these are the leakage from unimaginably powerful transmitters, beacons meant for communication across the cosmic deep. While natural explanations are far more likely, the sheer power and brevity of these bursts force us to confront the limits of our own imagination. Each new detection is a piece of a puzzle scattered across the universe, a clue to the most energetic and secretive processes shaping the cosmos. The hunt is on to catch them in the act, using networks of radio dishes across the globe to triangulate their source galaxies, hoping to see what other light, like X-rays or gamma rays, accompanies the radio flash. Solving the mystery of FRBs is not just about cataloging celestial explosions. It is a direct probe into the most violent and dynamic forces at work in our universe, forces we are only just beginning to hear. These cosmic flashes of radio energy are not the only strange signals challenging our understanding of the heavens. Far from the explosive violence of FRBs, a subtler but equally baffling mystery pulses from a single, otherwise ordinary star 1,500 light-years away. KIC 8462852, better known as Tabby's star, behaves like no other sun we have ever seen. Most stars exhibit a gentle, rhythmic dimming, the telltale signature of an orbiting planet passing in front of them. But Tabby's star does something far stranger. Its light drops by enormous amounts, up to 22%, in irregular, jagged dips that can last for days or even weeks. Then, just as unpredictably, it brightens again. This is not the clean, repeating curve of a planet, but the chaotic flicker of a candle in the wind. The star's bizarre behavior set off a firestorm of speculation and scientific detective work. The first, most natural explanations involved swarms of cosmic debris. Could a vast, dense cloud of comets be orbiting the star, blocking its light in these strange, uneven patterns? Or perhaps a recent planetary collision had created a massive, swirling disk of dust and rubble, casting these complex shadows? But each natural hypothesis ran into a problem. The amount of dimming is so extreme that it would require an implausible, almost unbelievable amount of material. A comet swarm large enough to cause such dips would be millions of times more massive than our own solar system's Kuiper belt, a structure of staggering proportions that challenges our models of solar system formation. This is where the most famous and controversial theory emerged. Could we be seeing the shadow of alien technology? The alien megastructure hypothesis suggests that an advanced civilization, a Type 2 on the Kardashev scale, might be building a vast array of energy collectors around their star, a Dyson sphere. Such a structure, even if only partially complete, would consist of gigantic panels or swarms of orbital habitats that would intermittently block the star's light in exactly these irregular, non-repeating ways. While captivating, this idea is treated as a hypothesis of absolute last resort. The scientific community has continued to search for more conventional answers, and over time, evidence has pointed toward a more likely, if still unusual, culprit. Detailed analysis of the starlight revealed that the dimming is more pronounced at blue wavelengths than at red ones. This is a classic signature of dust. Tiny particles smaller than a grain of smoke scatter blue light more effectively, letting the redder light pass through. This strongly suggests that the star is shrouded in a huge, uneven cloud of fine, circumstellar dust. The irregular dimming could then be explained by clumps of this dust orbiting the star in a chaotic, evolving disk, perhaps the aftermath of a shattered moon or a disintegrating planet. The true lesson of Tabby's star is not about finding aliens, but about the limits of our own perception. It revealed how quickly we can leap to extraordinary conclusions when faced with data that defies our expectations. It taught astronomers to be more agile, to consider a wider range of natural phenomena, and to develop new tools for classifying the strange and the unexpected. This single, flickering star became a masterclass in cosmic humility, reminding us that the universe is always more inventive than we are. And if dust around a single star can create such a profound puzzle, what mysteries await within the swirling hearts of the galaxies themselves? While we search for signals in the void, the cosmos sent us a messenger we never expected to touch our own celestial shores. In October 2017, a telescope in Hawaii spotted a faint point of light moving at incredible speed. It was not from our solar system. This was Oumuamua, the first known visitor from interstellar space, a scout from the vast ocean between stars. Its arrival was historic, but its properties were baffling. First, its shape. Based on the extreme way its brightness varied, astronomers concluded it was profoundly elongated, perhaps 10 times longer than it was wide. Think of a cosmic cigar or a pancake tumbling through the void, a shape unlike any known asteroid or comet in our own system. The second mystery was its motion. As it hurtled away from the sun, it accelerated slightly as if being gently pushed. Comets do this when their ices heat up and vent gas, forming a visible tail that acts like a natural rocket engine. But Oumuamua showed no tail, no coma of gas and dust, no visible outgassing at all. It was a rock that behaved like a comet but refused to look like one. So what was it? The debate ignited immediately. One camp argued it was a very peculiar comet after all. Perhaps it was made of very pure water ice or carbon monoxide ice that sublimated, turning directly from solid to gas, producing a faint, invisible jet that provided the push without creating a visible cloud of dust. Another, more exotic idea proposed that Oumuamua was a hydrogen iceberg. In the coldest, densest cores of molecular clouds, hydrogen could theoretically freeze solid. A chunk of this frozen hydrogen would vent the gas as it neared the sun, explaining the acceleration without leaving a dusty trail, since hydrogen is invisible in that state. Yet others suggested it was a shard of a Pluto-like world, a fragment of nitrogen ice blasted off a distant dwarf planet in some ancient cosmic collision. This could also account for its strange acceleration and lack of dust. And then, of course, there was the most speculative hypothesis. Could it be a piece of alien technology, a discarded light sail from a long-vanished probe? Its flattened shape and light-powered acceleration were at least consistent with this far-out idea, though most scientists consider it the least likely possibility, a reminder of how the unknown can spark our wildest imaginations. The true frustration is that Oumuamua is now gone, speeding out of sight, its secrets forever locked in its tumbling form. We had just a few weeks to study it before it vanished into the darkness from whence it came. Its brief visit taught us a humbling lesson. Interstellar space is not empty. It is littered with unseen travelers, and we have only just begun to notice them passing through our neighborhood. This single, silent rock forced us to expand our imagination of what natural objects can be, and it leaves us staring at the sky, wondering what the next visitor will look like. Oumuamua's silent passage highlights a deeper, more profound silence, one that has echoed for generations. With hundreds of billions of galaxies, each containing hundreds of billions of stars, the sheer number of potential worlds for life is staggering. The universe seems to offer every opportunity for other intelligent civilizations to arise, flourish, and fill the cosmos with their presence. Yet when we listen, we hear nothing but the natural hum of stars and gas. This is the Fermi Paradox, the unsettling contradiction between the high probability of alien life and the complete lack of any evidence for it. If the universe is so vast and old, where is everybody? One of the most sobering answers is the Great Filter hypothesis. This idea suggests that at some point between the emergence of life and the colonization of the galaxy, there exists a barrier, a step so difficult that almost every civilization fails to cross it. This filter could lie in our past. Perhaps the spontaneous origin of life from non-living chemistry is an event of such miraculous improbability that it has only happened once in our entire observable universe. Or maybe the leap from simple prokaryotic cells to complex eukaryotic life, a transition that took 2 billion years on Earth, is the true bottleneck. If this is the case, then we are utterly alone, the only conscious beings in the cosmos, having already passed through the filter. The more terrifying possibility is that the Great Filter lies in our future. Perhaps every advanced civilization, upon reaching a certain technological level, inevitably discovers a technology that leads to its own destruction. This could be nuclear annihilation, engineered pandemics, or a runaway artificial intelligence. In this scenario, the silence of the cosmos is a graveyard, a warning of a fate that awaits every species that rises too high. But destruction is not the only possibility. Another solution to the paradox suggests that intelligence itself may not be an evolutionary advantage in the long run. Perhaps civilizations advanced enough for space travel ultimately turn inward, creating immersive virtual realities so compelling that they lose all interest in the external, physical universe. Why brave the immense distances and dangers of interstellar travel when you can create a perfect paradise within a computer? To such a civilization, the stars would be irrelevant and they would be effectively invisible to us. There is also the possibility that we are simply not listening correctly, or that we are unable to recognize the signs. Our searches focus on radio waves and laser signals, technologies that we ourselves have mastered for barely a century. A civilization 1,000,000 years more advanced might use communication methods we cannot even conceive of, like manipulating neutrino streams or sending messages through quantum-entangled particles. Their technology might be so integrated with their environment that it is indistinguishable from natural phenomena. We might be surrounded by their artifacts, staring at their megastructures without recognizing them as anything other than strange stars or cosmic dust clouds. Perhaps the most humbling idea is that we are the new arrivals in an ancient, crowded cosmos. The universe is 13.8 billion years old, while human civilization is only a few thousand years old. Other intelligent species could have risen and fallen or transcended to a higher state of existence long before our sun even formed. We may be like ants arriving in a city that was abandoned eons ago, wandering through silent, crumbling ruins whose purpose we cannot fathom. The silence we perceive might not be emptiness, but the aftermath of a party that ended billions of years before we learned to listen. The truth behind the Fermi Paradox forces us to confront our own future. Are we on the cusp of passing a filter that has silenced every other voice? Or are we just beginning a journey that will one day see us become the silent, invisible elders of the galaxy? The answer will define not just our place in the cosmos, but whether we have a future there at all. The profound silence of the cosmos may be a question of information, a cosmic rule that seems to break down at the edge of reality. When anything crosses the event horizon of a black hole, it is gone forever, lost from our universe. According to Einstein's theory of general relativity, that object's information, the specific arrangement of particles that made it a book, a planet, or a person, is irretrievably crushed into the singularity. The black hole itself only remembers the total mass, electric charge, and spin. It is the ultimate cosmic shredder. Yet quantum mechanics, the rules governing the very small, has a fundamental and unbreakable law. Information can never be truly destroyed. It can be scrambled, hidden, or transformed, but the quantum information that describes every particle must, in principle, be recoverable. This creates a direct and violent contradiction between our two most successful theories of physics. How can both be true? Stephen Hawking discovered that black holes are not completely black. Due to quantum effects near the event horizon, they slowly radiate energy, losing mass over unimaginable eons until they potentially evaporate entirely. This is Hawking radiation, but here is the paradox. Hawking's original calculations suggested this radiation is completely random, a featureless thermal haze carrying no information about what fell in. If the black hole evaporates and disappears, the information it consumed would be lost forever, violating a cornerstone of quantum physics. So where does the information go? One leading idea, the holographic principle, proposes a truly mind-bending solution. It suggests that all the information about everything that falls into a black hole is not stored in its mysterious interior, but is somehow encoded on its two-dimensional surface, the event horizon. Think of the universe in 3 dimensions as a holographic projection from a two-dimensional surface, like a security chip on a credit card that holds all the data for a 3-dimensional image. When an object falls in, its information is smeared and stored as tiny, Planck-length pixels on this surface. The Hawking radiation that leaks out then slowly and chaotically carries this scrambled information back into the universe. The information was never truly inside the black hole. It was always painted on the wall, and the evaporation process is just a very slow and messy way of reading it back out. Another dramatic possibility involves wormholes or quantum entanglement. Every particle of Hawking radiation could be intricately connected or entangled with a partner particle that fell into the black hole long ago. This vast, invisible web of quantum connections might form a bridge, a wormhole, through which the information can eventually escape. Solving this paradox is not just an academic exercise. It strikes at the heart of whether the universe is fundamentally predictable and orderly. If information can be lost, then the past does not determine a single future, and reality itself becomes fundamentally random. The answer will likely require a theory of quantum gravity, a framework that unites the world of the very large with the very small, revealing the true nature of space and time. This cosmic puzzle forces us to ask if black holes are the ultimate vaults, or if they are the most complex libraries in existence, with a story written on a wall we can never see. That profound silence might be a question of timing, a cosmic clock that ticks differently everywhere you go. Our own experience of time is so intuitive, so linear, that it feels like an unchangeable river flowing from past to future. Yet physics suggests this river may be an illusion. At the most fundamental level, the equations that govern our universe, from Newton to Einstein to quantum mechanics, work perfectly well in reverse. There is no inherent arrow of time in the underlying math. So where does our relentless march from yesterday to tomorrow come from? The answer appears to be deeply tied to a concept called entropy, which is a measure of disorder in a system. The second law of thermodynamics states that the total entropy of an isolated system always increases over time. Think of a drop of ink in a glass of water. It starts in a state of low entropy, concentrated and ordered. Then it diffuses, spreading out into a uniform, high-entropy mixture. This process is irreversible. The universe itself seems to be following this same rule on a cosmic scale, moving from the highly ordered, low-entropy state of the Big Bang toward a final, high-entropy state of maximum disorder, what we might call the heat death. Our perception of time's arrow, the reason we remember the past but not the future, may simply be a consequence of us being caught in this universal slide toward greater chaos. But is this the whole story? What if you could step outside this cosmic current? According to Einstein's theory of relativity, time is not a universal constant. It is a flexible dimension woven together with space into a single fabric called space-time. This fabric can be stretched and warped by gravity and velocity. For a civilization that mastered interstellar travel at a significant fraction of light speed, time would literally slow down for them relative to the rest of the universe. A journey that felt like 10 years for the crew on a starship could see 100 years pass on their home world. They would return to a future that had moved on without them. The effect is even more extreme near a black hole, where gravity warps space-time to an incredible degree. An observer watching from a safe distance would see a clock falling toward the event horizon slow down, ticking more and more slowly until it appears to freeze completely at the point of no return. For the one falling in, however, their own clock would seem to tick normally. This means that for a hypothetical civilization living on a planet orbiting close to a black hole, time would crawl from our perspective. They could experience a single generation while entire galactic empires rise and fall in the universe outside. This raises a dizzying possibility. If time is so malleable, so dependent on perspective and motion, then what we call the present moment may have no universal meaning. Your now and the now of a being in a distant galaxy moving at high speed could be completely different. The flow of time we feel so deeply in our bones might not be a fundamental feature of the cosmos, but rather an emergent property, a story our conscious minds tell us as we navigate a universe slowly unraveling from order to disorder. Unlocking the true nature of time could be the final step in weaving together gravity and quantum mechanics, revealing a reality where past, present, and future exist simultaneously in a single frozen block. This strange relationship between time and observation leads us to a mystery that lies at the very foundation of reality. The quantum world operates by rules that seem to defy common sense. An electron is not a tiny, solid ball orbiting a nucleus. Until we measure it, it exists in a blurry cloud of possibilities, a superposition of being in many places at once. This is its wave function, a mathematical description of all its potential states. The moment we look, however, this cloud of possibilities instantly collapses. The electron snaps into a single, definite location, becoming a particle we can point to. This abrupt shift from fuzzy probability to sharp reality is the quantum measurement problem. Why does the simple act of observation force the universe to make a choice? What or who actually counts as an observer? Does it require a conscious human mind, or is any interaction with the larger environment sufficient? This is not just a philosophical puzzle, it is a gaping hole in our understanding of how the world works. One interpretation suggests there is no collapse at all. The many worlds theory proposes that every possible outcome of a quantum event actually happens. The universe splits, branching into a near infinite number of parallel realities. In one branch, you see the electron on the left. In another, an alternate version of you sees it on the right. There is no single outcome, only an ever-proliferating multiverse where every possibility is realized. Another idea, known as objective collapse, argues that the wave function collapses spontaneously when a system becomes too large or complex, a physical process we have yet to discover. Then there is the Copenhagen interpretation, which simply accepts the collapse as a fundamental, unexplained axiom of nature. The implications ripple outward, touching the nature of reality itself. Is the definite world we see an illusion, a single thread selected from a vast tapestry of potentialities? The answer is not merely academic. Our entire future in quantum computing hinges on this very question. Quantum computers rely on maintaining superposition, on keeping qubits in that delicate state of multiple possibilities to perform calculations that are impossible for classical machines. Understanding and controlling the collapse of the wave function is the difference between a machine that can crack any code and one that decoheres into useless noise. It is the frontier where philosophy meets engineering, where our deepest questions about consciousness and reality may one day be answered not by philosophers, but by the silent hum of a quantum processor. Gravity is the force that holds entire galaxies together, yet a simple refrigerator magnet can overcome the entire Earth's gravitational pull on a piece of metal. This is not just a quirky fact, it is a profound cosmic mystery known as the hierarchy problem. The strength of gravity is not just a little weaker than the other fundamental forces, it is weaker by a factor of 1 followed by 40 zeros. To put that staggering number into perspective, the difference in strength between gravity and the electromagnetic force is greater than the difference in size between a single proton and the entire observable universe. This is the most extreme fine-tuning in all of nature, and it suggests our current model of physics is dramatically incomplete. Why would the universe create a force responsible for the majestic dance of planets and stars, only to make it almost vanishingly feeble at the level of atoms and particles? The leading theories that attempt to solve this puzzle are as breathtaking as the problem itself. One compelling idea is supersymmetry. This theory proposes that every known particle has a hidden super-partner twin. The electron would have a selectron, the quark would have a squark, and so on. In a perfectly supersymmetric universe, the quantum contributions of these partner particles would perfectly cancel out the enormous energy that makes gravity seem so weak, solving the hierarchy problem with an elegant symmetry. The catch is that we have not found any of these superpartners, which implies that if supersymmetry is real, it is a broken symmetry, and these particles must be incredibly heavy, perhaps within reach of the next generation of particle colliders. An even more radical solution involves the fabric of space itself. What if gravity only seems weak because it is not confined to our three-dimensional world like the other forces? The theory of large extra dimensions suggests that our universe may have more than the three spatial dimensions we experience. While electromagnetism and the nuclear forces are trapped on a three-dimensional membrane, gravity could be leaking out into these hidden higher dimensions. From our perspective, this leakage would make gravity appear diluted and weak, like a drop of ink spreading through a vast volume of water. In this scenario, gravity might be just as strong as the other forces, but its true power is lost in dimensions we cannot perceive. This theory makes a startling prediction. If we can probe matter at incredibly small distances, we might find that gravity suddenly becomes stronger, a sign we are sensing its full force before it leaks away. Future particle accelerators, more powerful than any we have yet built, could potentially create microscopic black holes, tiny gravitational whirlpools that would be the ultimate proof of these extra dimensions. The hierarchy problem is not an abstract curiosity, it is a direct challenge. It tells us that our understanding of the cosmos is built on a foundation with a glaring crack, a crack that may open into a much larger and stranger reality. This staggering mismatch between prediction and reality is the cosmological constant problem. Our most successful theories of the quantum world suggest that empty space should be bursting with a violent, seething energy. Every tiny point in the vacuum is a temporary frenzy of virtual particles flickering in and out of existence, and all this activity should add up to a colossal repulsive force. The calculations are clear, but the result is a number that is wrong by a factor of 1 followed by 120 zeros. It is not just a little mistake, it is the most spectacular failure of theoretical prediction ever made. To grasp the scale of this error, imagine predicting that a single breath of air would be enough to inflate a balloon to the size of the entire observable universe. The actual result, the gentle acceleration we call dark energy, is that the breath only makes the balloon expand by less than the width of a single atom. The universe is almost unimaginably quieter and calmer than our physics says it should be. So why is the vacuum of space so placid? Why does this predicted storm of energy cancel out to almost perfect zero? One possibility is an almost perfect but not quite total cancellation. Perhaps the quantum buzz contributes a huge positive value, while some other unknown physical field contributes a nearly identical huge negative value. The two titanic forces would balance each other out, leaving behind only the tiny, leftover residue we measure as dark energy. The problem is that this requires a level of fine-tuning that seems absurd. It would be like two opposing armies, each with 1 trillion soldiers, fighting to the last man, and ending with exactly 1 soldier left standing on one side. The precision needed for such a balance is beyond belief. Another, more radical idea is that we are thinking about the vacuum completely wrong. Perhaps the quantum fluctuations that we calculate do not actually gravitate in the way we assume they do. Maybe the rules of gravity and quantum mechanics, when properly united, will show that this frantic activity of virtual particles simply does not contribute to the cosmic expansion. The vacuum would then be fundamentally stable, and dark energy would arise from an entirely different source, like a slowly evolving energy field we call quintessence. Solving this problem is not just about fixing a calculation. It is about finding the missing piece that connects the world of the quantum to the destiny of the cosmos. The answer will rewrite our understanding of nothingness itself, revealing why the void is not a roaring inferno, but a gentle, accelerating push into the future. That same violent quantum vacuum, whose silence baffles our physicists, is constantly being pierced by messengers of unimaginable power. For over a century, we have known that Earth is under a continuous, invisible rain. These are cosmic rays, not rays of light, but atomic nuclei stripped of their electrons and accelerated to nearly the speed of light. They are individual particles carrying energies that dwarf anything we can create in our greatest machines, like the Large Hadron Collider. The most common cosmic rays are protons, the nuclei of hydrogen atoms, but we have detected the nuclei of every element in the periodic table, from helium to uranium, all hurtling through the galaxy. They are the fastest, most energetic pieces of matter we have ever observed, yet their origin is one of the longest-standing puzzles in astrophysics. Where are the universe's natural particle accelerators, and how do they fling a single, solitary proton with the kinetic energy of a professionally thrown baseball? For many cosmic rays, the source is relatively close to home. Within our own Milky Way, the shockwaves from supernova explosions are prime suspects. When a massive star dies, it blasts its outer layers into space at thousands of kilometers per second. This creates a colossal, expanding shell of gas and a powerful shock front, a natural particle accelerator stretching for light years. Protons and other atomic nuclei can become trapped, bouncing back and forth across this magnetic shockwave like a ping-pong ball, gaining a little more speed with each crossing until they are eventually ejected at a significant fraction of light speed. These galactic cosmic rays are responsible for a steady background drizzle of high-energy particles. But the most extreme cosmic rays, the true monsters, demand a far more powerful engine. Their energies are millions of times greater than those produced in supernova remnants. To find their source, we must look beyond our galaxy to the most violent objects in the universe. The prime candidates are active galactic nuclei, the supermassive black holes at the centers of galaxies that are actively feeding. As vast quantities of matter spiral into the black hole, it doesn't all fall in. Some is channeled by immense magnetic fields into jets of plasma that shoot out from the poles at nearly light speed, stretching for millions of light years into intergalactic space. A particle caught in one of these relativistic jets could be accelerated to energies that are almost incomprehensible. Yet even these cosmic powerhouses were called into question by one particular event. In 1991, a detector in Utah recorded something that should not exist. A single particle struck the atmosphere with an energy of about 300 exa-electron volts. It was dubbed the "Oh my God" particle. This one subatomic proton was traveling so fast that, due to special relativity, it possessed kinetic energy equivalent to a bowling ball dropped from waist height. It had the energy of a major league fastball but compressed into a single, fundamental particle. The mystery is profound. According to a rule called the GZK cutoff, such an ultra-high-energy particle should not be able to travel very far through the cosmos. The universe is not completely empty. It is filled with the dim glow of the cosmic microwave background radiation. A proton with the energy of the "Oh my God" particle should collide with these background photons in a violent interaction that would rapidly sap its energy over distances of 100 million light years or so. Its existence means it must have originated within our local cosmic neighborhood, a relatively empty region of space where no known object, no active galactic nucleus or colliding galaxy clusters is powerful enough to have created it. So what did the "Oh my God" particle remains an enigma, a ghost from a source we cannot identify. It hints at astrophysical processes we have not yet dreamed of, or perhaps at the decay of exotic relics from the Big Bang, like cosmic strings or super-heavy dark matter particles. The hunt for these extreme cosmic rays continues with vast observatories that cover dozens of square miles, using the Earth's own atmosphere as a detector. When an ultra-high-energy cosmic ray hits the air, it creates a cascade of secondary particles, a sprawling shower that these arrays can map to reconstruct the original particle's energy and direction. Each one is a clue, a piece of shrapnel from the most violent explosions and accelerators in the cosmos. and their story is written in the faint flashes of light they create in the dark night sky. That profound silence we perceive might be the most honest answer the universe can give. The Fermi Paradox forces us to confront a deeply unsettling possibility, one that challenges our cosmic significance. What if the complex chain of events that led to our existence is not a common recipe, but a singular, miraculous fluke? This idea is known as the rare earth hypothesis, and it suggests that while simple microbial life might be widespread, the emergence of intelligent, technological civilizations like ours requires such a precise and fragile sequence of conditions that we might be the only one in our entire galaxy. Consider our own planet's history. It is not just about being in the habitable zone, the so-called Goldilocks region where water can remain liquid. Earth's journey to fostering intelligent life was a precarious obstacle course. We benefited from a massive moon formed in a violent collision with a Mars-sized protoplanet. This lunar partner stabilized our planetary tilt, preventing chaotic climate swings that would have made long-term evolution impossible. Our planet also has an active geological engine, a molten core that generates a powerful magnetic field. This invisible shield deflects the sun's deadly radiation, protecting our atmosphere from being stripped away and allowing life to thrive on land. Even our position in the galaxy is peculiarly safe. We orbit in a relatively quiet suburban spiral arm, far from the violent, sterilizing core where supernova and gamma-ray bursts are commonplace. A planet too close to the galactic center would be routinely scoured by apocalyptic radiation, resetting the evolutionary clock every few million years. Then there is the story of life itself. For over 2 billion years, Earth was inhabited only by simple, single-celled organisms. The leap to complex, multicellular life was a monumental evolutionary hurdle, one that may have required another set of improbable accidents. What if the peaceful, stable conditions necessary for intelligence to emerge and then develop technology for eons are the universe's true rarity? In this view, every planet with life might be an isolated island, separated by oceans of space and time, with most islands never progressing beyond a microbial stage. The silence is not a puzzle, it is a reflection of a galaxy where worlds like Earth and minds like ours are the ultimate cosmic treasures. This possibility carries a profound weight of responsibility. If we are alone, then the flame of consciousness, the ability to look up and question the stars, is entirely in our hands. We are not just a species, we are the universe becoming aware of itself. The choices we make, the future we build, would carry an importance we can scarcely imagine, for we would be the only ones writing the next chapter of this cosmic story. Our universe runs on two sets of rules that cannot both be correct. Einstein's theory of general relativity paints a beautiful picture of gravity as the smooth curvature of space-time, a cosmic fabric warped by planets and stars. It perfectly predicts the orbit of Mercury, the bending of starlight, and the existence of black holes. Yet this elegant geometric tapestry completely unravels in the subatomic world. Quantum mechanics reveals a reality built on chance and discrete packets of energy, where particles pop in and out of existence and forces are transmitted by messenger particles. To merge these two masterpieces into a single theory of quantum gravity is the defining challenge of our time, a puzzle that has consumed the brightest minds for nearly a century. The core of the conflict lies at the extremes, at the center of a black hole or at the very moment of the Big Bang. General relativity predicts a point of infinite density, a singularity where the laws of physics simply break down. This is a clear signal that our theory is incomplete, that we are missing the quantum rules that govern gravity itself. How can we describe the fabric of space-time if it becomes a seething, probabilistic foam at the smallest possible scales? One of the most ambitious answers is string theory. It proposes a breathtaking shift in perspective. The the fundamental constituents of the universe are not point-like particles, but unimaginably tiny, vibrating loops of energy, smaller than a proton by a factor of a trillion trillion. Just as different vibrations of a violin string create different musical notes, the distinct resonant patterns of these strings give rise to all the particles and forces we see. The graviton, the hypothetical quantum particle of gravity, emerges naturally from one specific vibrational mode. The cost of this elegant unification, however, is a radical expansion of reality. String theory only works mathematically in a universe with 10 or 11 dimensions. We experience only 3 of space and 1 of time. Where are the others? The theory suggests they are curled up or compactified into shapes so minuscule that they are forever beyond our direct perception. The specific way these extra dimensions are folded determines the very laws of physics in our visible universe. Another profound contender is loop quantum gravity. It takes a different path, focusing directly on the structure of space itself. It proposes that space is not a smooth, continuous backdrop, but is woven from a fabric of finite, indivisible loops. Think of the fabric of reality as a chainmail tunic built from interlinked rings. These loops form a network of relationships, a spin foam, and the quanta of space are these individual links. In this theory, there is no such thing as a singularity. Instead of an infinitely dense point, the core of a black hole is a bridge to another region of space-time, and the Big Bang was not a true beginning, but a great bounce from a previous cosmic phase. The implications of solving this conundrum are not just philosophical. A working theory of quantum gravity would unlock the secrets of the universe's first moment. It would tell us if the Big Bang was a unique beginning or part of an endless cycle. It could reveal what truly happens inside a black hole, resolving the paradox of information loss. For our distant future, such a theory might offer the ultimate form of energy control, allowing us to manipulate the fabric of space-time itself. The path to this holy grail is paved with a formidable challenge, a test of prediction so difficult it has stalled progress for decades. That search for a unified theory of physics leads to one of the most radical reimaginings of reality ever proposed. The universe we experience, with its rich three-dimensional depth, might be nothing more than a magnificent illusion. This is the holographic principle. The idea suggests that all the information needed to describe our cosmos, every galaxy, every star, every one of us, is actually encoded on a distant, two-dimensional surface that surrounds us. We are not solid beings in a voluminous space, but a kind of projection, like a three-dimensional hologram emerging from a flat, two-dimensional screen. The roots of this staggering idea are not in philosophy, but in the hard physics of black holes. When anything falls into a black hole, it vanishes behind the event horizon, and according to classical physics, its information is lost forever. But quantum mechanics forbids such destruction. In the 1970s, physicist Jacob Bekenstein made a crucial discovery. He realized that a black hole's entropy, which is a measure of its hidden information, is not proportional to its volume as you might expect. Instead, it is proportional to the surface area of its event horizon. Think of that for a moment. The amount of information a black hole can contain is determined by the two-dimensional skin of its boundary, not by the three-dimensional space within it. It is as if the entire content of the black hole's interior is painted, pixel by pixel, onto its surface. This was the first clue that the fundamental description of a region of space might reside on its boundary, not within it. Later, other physicists like Gerard T. Hooft and Leonard Susskind expanded this concept to the entire universe. If the maximum information in any region of space is defined by its surface area and not its volume, then our intuitive sense of a third dimension might be emergent. It is a cosmic sleight of hand. How could this possibly work? Imagine a high-resolution security hologram on your credit card. The flat, shiny surface contains all the data necessary to project a three-dimensional image that you can look around. The holographic principle suggests our universe operates on a similar, though infinitely more complex, scale. The entire cosmos we see could be a projection from a vast, two-dimensional shell at the edge of our observable universe. Every event, every particle interaction is just a representation of information processing happening on that remote surface. The implications are as profound as they are bizarre. It would mean that reality is fundamentally digital, composed of tiny, indivisible bits of information, much like the pixels on a screen. The smooth continuity of space and time would be an approximation, an emergent property from the frenetic interactions of these fundamental information bits. This could finally provide a framework for uniting gravity with quantum mechanics, by showing that gravity itself is not a fundamental force, but an emergent phenomenon, a consequence of the way information is organized and entangled on the cosmic horizon. For us, living inside the projection, the world feels utterly real and three-dimensional. But the holographic principle hints that the true, fundamental workings of the cosmos are happening on a flat, distant surface we can never touch, a reality where the third dimension is merely a grand and convincing illusion. This final cosmic mystery is not written in the stars, but in the very code of reality itself. The simulation hypothesis asks a question so radical it redefines everything we take for granted. What if our universe, with all its galaxies, stars, and conscious minds, is not the base level of existence, but an incredibly sophisticated simulation, a digital construct running on the computer of a vastly more advanced civilization? While it sounds like science fiction, this idea is a serious philosophical and scientific thought experiment, one that forces us to confront the ultimate nature of our own reality. The argument begins with a simple projection of technological progress. If our own civilization continues to advance, we might one day develop the computing power to run detailed simulations of entire worlds, complete with conscious beings who believe their existence is real. A sufficiently advanced civilization might not run just one such simulation, but billions of them, each a unique experiment or form of entertainment. If that is the case, then the vast majority of conscious experiences in the cosmos would be simulated, not base reality. Statistically, it is more likely that we are living in one of those countless simulations than in the one original universe. So how could we possibly test such an outlandish idea? Some physicists suggest looking for glitches in the matrix. Just as a video game has a finite resolution, our universe might have a fundamental pixelation at the smallest possible scale. We might find evidence of this in the way the highest energy cosmic rays behave, or in subtle anomalies in the cosmic microwave background, a sort of cosmic save file. Others propose that the very laws of physics might contain hints of their engineered nature. The speed of light, for instance, acts like a maximum processor speed, a limit on how fast information can travel within the simulation. The oddities of quantum mechanics, where particles exist in multiple states until observed, could be seen as a rendering optimization technique, a way for the simulation to save computational resources by only calculating the precise details of a system when someone is looking. The philosophical implications are staggering. If we are in a simulation, then free will, the soul, and the meaning of life itself become profoundly different questions. Are our choices our own, or are they the output of a deterministic algorithm? Is the universe fine-tuned for life because the programmers designed it that way? This hypothesis does not necessarily make our existence less meaningful. Instead, it suggests that our reality, whether base or simulated, operates on a set of consistent rules that we can explore, understand, and even appreciate. The emotions we feel, the love we share, and the wonders we discover are no less real to us. For our future, the simulation hypothesis presents both a warning and an aspiration. It warns that if we ever create such simulations ourselves, we bear an immense ethical responsibility for the conscious lives within them. and it aspires to a future where humanity might one day become the creators, the gods of new digital universes, continuing the grand cycle of cosmic evolution in a realm of our own design. Ultimately, whether our universe is simulated or not, the act of questioning its fundamental nature is what defines our unique place within it. We are the part of the cosmos that has awakened, that looks back and asks, what is this place and why am I here to see it? From the first impossible second to the final, silent fate of reality, the cosmos is woven from enigmas that refuse to surrender their secrets easily. These 30 mysteries are far more than abstract scientific curiosities. They are the living, breathing frontiers of human knowledge, the very boundaries that define our quest to comprehend our own existence. Each puzzle we have explored, from the ghostly pull of dark matter to the silent scream of the wow signal, represents a doorway. On the other side lies not just an answer, but a revolution. Solving them will not merely update our textbooks, it will fundamentally reshape our civilization. The technologies born from understanding dark energy could one day grant us mastery over the expansion of space itself. Unraveling the nature of quantum gravity might provide the key to limitless energy or travel between the stars. The philosophical implications are just as profound. Discovering we are alone in the universe would imbue our existence with an immense and solemn responsibility, while finding we are not would forever shatter our cosmic solitude. Our entire way of life, from how we power our cities to how we see our place in the grand scheme of things, hinges on the solutions to these cosmic riddles. The journey through these mysteries is a reminder that we are the universe awakening to itself, asking questions of the void and listening intently for the echoes. So we turn the question to you: which of these cosmic puzzles captures your imagination the most? Is it the haunting silence of the Fermi Paradox or the ghostly architecture of the cosmic web? Let us know in the comments below, and if this journey to the edge of understanding has sparked your curiosity, be sure to subscribe for more explorations into the deepest wonders of our reality.